Hey everyone, and welcome back to the deep dive. Today we're going to be diving into something pretty wild. Um, Physics-informed neural networks,
PINNs.
PNNs, right? Short and catchy. But seriously, these things sound like something straight out of science fiction.
You're not wrong to think that. We're talking about AI that doesn't just crunch numbers, but actually gets the lives of physics.
Okay, hold on, back up a sec. You provided me with some seriously cool research on this, so I know we're not just making this up.
Right, this is real deal stuff.
But for our listeners who are just tuning in, let's start with the basics. What exactly are we talking about when we say physics-informed neural networks?
Okay, so imagine this. You've got a computer program, and it can analyze data, sure, but it can also understand, like really understand, the fundamental laws of physics.
Okay, so it's not just spitting out numbers, it's like thinking like a physicist.
Exactly. It's like we're taking the power of neural networks, the kind of stuff that powers facial recognition, and we're giving them a crash course in Physics 101.
And not just any physics class, but like the kind where they actually have to ace the exams.
Right, because we're talking about embedding those physical laws into the very core of how these networks learn and make predictions.
Now, the research paper we're looking at is Scientific Machine Learning through PINNs. And let me tell you, it's dense. But one thing that caught my eye was this idea of a loss function. I'll be honest, my brain kind of stalled out there.
Yeah, it sounds a bit intimidating, but it's actually a pretty elegant concept. Basically, the PIN is learning by trying to minimize this loss function, and that happens when its predictions line up with what we know to be true according to physics.
So it's like the closer its predictions are to reality, the lower its score on this loss function, and that's how it knows it's doing a good job.
Precisely. It's like rewarding a dog for doing a trick, right? The treat is minimizing that loss function.
Okay, that makes a lot more sense. So it's learning by trial and error, but it's got the laws of physics acting as guardrails, making sure it's headed in the right direction.
Exactly. And this isn't like some brand new idea either. The research paper mentions some early work from way back in the 90s.
Oh, really? I thought this was all cutting edge, hot off the press stuff.
Well, it is in a way, but the roots go deeper than you might think. It wasn't until around 2019, though, that things really took off.
What happened then?
A couple of researchers, Racy and others, they published some groundbreaking work that really opened everyone's eyes to just how powerful PNNs could be.
And I'm guessing that kicked off a whole wave of new research and development.
Oh, absolutely. It's like someone opened the floodgates. Suddenly, everyone's trying to build their own PNNs, refine them, find new applications, the whole 9 yards.
And speaking of different types of PNNs, the research mentions there isn't just one flavor of these things, right?
Oh, you are absolutely right. It's more like you walk into an ice cream shop and they've got a flavor for every taste bud. You've got your feed-forward networks, your convolutional networks. Heck, you've even got recurrent networks that are designed to understand things that change over time.
It's like having a whole toolbox full of specialized PNs, each one perfect for a particular type of physics problem.
That is a fantastic way to put it. And the choice of which PNN to use, well, that all depends on the specific problem you're trying to solve.
It's like picking the right tool for the job. Except in this case, the tools are these incredibly complex, physics-savvy AI algorithms.
And just like with a set of tools, even within each type of PIN, there are variations, right? Subtle differences that can make a big impact.
Yeah, the paper mentioned something about activation functions. I'll admit, I skimmed over that part a bit.
Ah, yes, the activation functions. Those are important for sure. Choosing the wrong activation function can be a bit like, how do I put this? Imagine putting diesel in a gasoline engine.
Okay, yeah, that's not going to end well.
Exactly. It's just not going to work the way it's supposed to. The activation functions, they're like the fine-tuning, making sure the PIN is operating at peak performance.
So we've got all these different flavors of PINs, but what are they actually good at? I mean, the research paper mentioned some pretty mind-blowing examples.
Oh yeah, we're not just talking about some theoretical exercise here. PINs are already making waves in a bunch of different fields. One that really jumped out at me was fluid dynamics.
Oh, right, like predicting how liquids and gases behave. Isn't that notoriously difficult to model accurately?
It definitely can be, yeah. Especially when you start getting into things like turbulence and shock waves.
Yeah, those always trip me up in physics class.
Right. Well, PINs, they seem to have a knack for it. They can capture those complex behaviors with a level of detail that traditional methods really struggle with.
Okay, now that's something I can wrap my head around.
Yeah.
So instead of just trying to crunch through a bunch of equations, the PIN is actually learning the underlying physics of how these fluids move and interact.
Exactly. And that opens up some really wild possibilities. Imagine being able to design quieter supersonic aircraft.
Oh, wow. Now that would be a game changer.
Right. Or think about optimizing combustion engines for better fuel efficiency, all thanks to these PNNs that can model those incredibly complex processes with such precision.
So we're not just talking about like incremental improvements here. We're talking about potentially revolutionizing entire industries.
Potentially, yeah. And it goes even beyond that. The paper hinted at this, but PNNs could also help us unlock some scientific mysteries that have stumped us for years.
Oh, like what?
Well, one example that comes to mind is understanding turbulent plasma in a fusion reactor.
Fusion reactors. That's like the holy grail of clean energy,
Pretty
right?
much. And it all hinges on being able to control this incredibly hot, incredibly chaotic plasma.
Which I'm guessing is no easy feat.
You got that right. Traditional methods, they kind of hit a wall when it comes to modeling something that complex. But PNNs, they offer a whole new approach.
So they could be the key to finally unlocking fusion energy.
They could be a part of it, yeah. And that's just one example. There's a lot of buzz about using PNNs to accelerate drug discovery, design new materials, all sorts of cutting-edge stuff.
Okay, this is blowing my mind a bit, but let me ask you this.
Mm.
How accessible is this technology? Is it just limited to, like, top-tier research labs with supercomputers? Or could someone like me, with a decent understanding of AI and physics, actually build a PN?
You might be surprised. While building a PNN from scratch can be pretty intense, there are now open source tools out there that can really streamline the process.
Wait, seriously, so it's not just theoretical research locked away in ivory towers?
Not anymore. Libraries like DeepXDE and NeuralPDE-JL, they provide frameworks and pre-built components that take a lot of the heavy lifting out of designing, training, and testing PNNs.
That's amazing. It seems like the barrier to entry is getting lower all the time. But even with these tools, I imagine there are still challenges, right? Like, I can't imagine it's all smooth sailing from here on out.
Oh, for sure. PNNs are powerful, but they're not magic. One of the biggest challenges is making sure they actually converge to the correct solution.
Converge. What do you mean by that?
So remember how we talked about that loss function and how the PNN is trying to minimize it? Well, sometimes it can get kind of stuck in a solution that's not actually the best one.
So it's like hitting a dead end in a maze.
Exactly, and that's where things get tricky. Researchers are developing new techniques all the time to help guide PNNs toward those optimal solutions, but it's still an ongoing area of research.
So it's not enough to just feed a bunch of data into a PNN and let it loose. You need to kind of keep an eye on it, make sure it's on the right track.
Exactly. It's like anything else, right? You need the right tools, but you also need the skill and the know-how to use them effectively.
And I imagine that as you try to tackle bigger, more complex problems with PNNs, the computational demands must get pretty intense.
Oh, absolutely. Scalability, that's another big one. We need to find ways to make PNs more efficient, more capable of handling massive data sets and those really hairy equations.
Because right now, it sounds like we're just starting to scratch the surface of what these things can do.
We are, really, but that's what makes this whole field so exciting. There's so much potential here, so much still to be discovered.
So we've talked about the potential, the challenges, but what about the big what if? I mean, if we've got these PNNs that can already model things like shock waves and plasma, what's next?
Mm.
Could they actually lead us to discover new laws of physics?
That's the really mind-blowing part, isn't it? We're not just teaching these PNNs to, mimic what we already know.
Right.
We're giving them the tools to potentially uncover stuff we haven't even dreamt of yet.
It's like, imagine giving a superpowered telescope to a computer and saying, go explore the cosmos and tell us what you find.
Mm.
But in this case, it's like the computer's exploring the very laws of physics themselves.
Exactly. And I mean, I know it sounds like something straight out of science fiction, but the potential is there.
Totally. So as we train these PNNs on bigger and bigger data sets, more complex problems,
Right?
who knows what they might find?
They might stumble upon some weird anomaly, some subtle correlation that, maybe we just miss.
Because our brains aren't wired to see it.
Exactly. Our brains just haven't evolved to process information on that scale.
That's incredible. But it also kind of begs the question, what does it mean for us, for humanity, if we've got AI making these fundamental scientific discoveries? Do we just, kick back and let the machines do all the thinking?
I get that. It's a question a lot of people are wrestling with. And not just in physics,
Right.
but personally, I'm optimistic.
Okay, good.
I see PINNs as, a powerful new tool in our arsenal.
Not a replacement for scientists, but a partner.
Exactly. A collaborator. It's like, think of it this way. PINNs can handle the heavy lifting.
Sifting through mountains of data.
Yep. identifying patterns, even suggesting hypotheses.
And that frees us up to do what we do best.
Right. To interpret those findings, to come up with new theories, to ask even bigger, more mind-blowing questions.
It's like this beautiful partnership, human intuition and creativity combined with the raw power of these pin ends. It makes me super hopeful for the future of science.
Me too. We're on the verge of a whole new era of discovery, and pin ends are leading the charge.
Well, on that note, a huge thank you to you for guiding us through this deep dive into the world of pins. I feel like my brain is bursting with new ideas.
The pleasure was all mine, honestly. And to everyone listening, keep that curiosity alive. Keep asking those big what-if questions, and who knows what amazing discoveries await us, right?
And that's a wrap on this episode of The Deep Dive. Until next time, stay curious, my friends.